Hi, thanks for joining me today. I've got a beginner-friendly problem which was shortlisted for the 2012 IMO. It's a number theory problem, and the fact that it was shortlisted for the IMO suggests that it's a challenging problem, but the solution is relatively easy to follow and doesn't require much prerequisite knowledge. Anyway, what is the problem? We call a set of integers A admissible if it has the following property. Whenever we take two elements x and y in A, where possibly x equals y, then this number here must also be in A. So x squared plus k times xy plus y squared must be in A for every integer k. We want to determine all pairs m and n of non-zero integers such that the only admissible set containing both m and n is the set of all integers. So obviously the set of all integers is an admissible set. And we want to know for which integers m and n are there such that the only admissible set containing both m and n is only the set of all integers. Okay, so if you want to have a go at this problem, and I encourage you to do so, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so I claim that the solution is when m and n are co-prime. So in other words, they share no common factors. So to prove this, I want to prove both directions. So I want to prove firstly that if m and n aren't co-prime, then there is a non-trivial admissible set containing both m and n. And then I want to prove the other direction, that if m and n are co-prime, then there is no non-trivial admissible set containing both m and n. So let me first suppose that m and n aren't co-prime. So in other words, they have a greatest common divisor d, and d is strictly bigger than 1. Then what I'm going to do is simply write down an admissible set containing both m and n, and that will be the set of multiples of d. So it's going to contain 0, d, 2d, and so on, but also the negative multiples as well. And since d is strictly bigger than 1, this set, for example, won't contain the number 1, because 1 is somewhere between 0 and d, so this thing here is not the set of all integers. So firstly, it's a non-trivial set. Well, if it is an admissible set, it's a non-trivial admissible set. But we do need to check that it is an admissible set, but this is kind of obvious. If you take any two elements in this set, if we call it A, they're both going to be multiples of d. And so this quantity here, regardless of what k is also going to be a multiple of d. You know, if x is a multiple of d, then x squared will be a multiple of d. This thing will also be a multiple of d, and so will that. And if you're adding a bunch of multiples of d together, this is also going to be a multiple of d. So it's going to be some number in this set. So this is definitely an admissible set, and because it doesn't contain the number 1, it is not the set of all integers, and therefore a non-trivial set. And therefore, if m and n are not co-prime, then we know that there is at least one non-trivial admissible set. Now what we want to do is prove the other direction, and that is if m and n are co-prime, then there is no non-trivial admissible set containing both m and n. Okay, so now we're going to have a look at what happens when m and n are co-prime. And so what we want to do is suppose we have an admissible set A, which contains both m and n, and we want to prove that therefore A must be the set of all integers. So I'll put that in brackets. Our goal is to prove that A has to be the set of all integers. So to do this, we're going to make a couple of observations about what it means for a set to be admissible. And the first thing is this thing in brackets here. We're allowed to have x being equal to y. So what happens then? So if we have an element x in our set A, in our admissible set A, then x squared plus k times x plus x squared must also be an x for all integers k. But now this thing here is just k plus 2 times x squared, and this again has to be an a for any integer k. But if k is allowed to be any integer, then it's not too difficult to see that k plus 2 could also be any integer as well. And so this is in fact just saying that k times x squared is an a for all integers k. Okay, so if I have an element x in my set A, then I know that k times x squared is also in A for all integers k. That's one thing I notice. Another thing I notice is that if I just set x and y to be any elements in A, they don't have to be the same, and I look at the case when k equals 2, I see that if x and y is in A, then x squared plus 2xy plus y squared, which is more famously known as x plus y all squared, is in A. So in other words, if I have two elements in my set x and y and I add them up and then square them, that should also be in my set A. So I can combine these two facts here to get to our goal that A has to be the set of all integers. How can I do that? And it actually comes from from proving that the number 1 must be in A. Because if 1 is in A, then what we can do is just use this fact here and say that just by setting x equal to 1, we must have that k times 1 squared, which is obviously just k, must also be in A for any integer k. And then just by choosing k to be any integer we want, we can prove that A has to therefore be the set of all integers. So all I need to do is prove that the number 1 is in A. And to do that, I'm going to use the fact that m and n are co-prime. Because m and n are co-prime, it actually means that m squared and n squared are co-prime as well. And now what I'm going to do is use Bézieux's lemma, and this is a famous result from number theory. If you've not seen it before, I encourage you to look it up and see where it comes from, but I'm just going to assume it here. And Bézieux's lemma tells us that there are integers a and b such that a times m squared plus b times n squared equals 1. Okay, we're almost there in proving that 1 is in A. Firstly, m is in A and n is in A. And therefore, by looking at this rule again, I must have that any number times m squared and any number times n squared is also in A. And therefore a times m squared is in A, and b times n squared is in A. So I'm adding up two elements that are both in A, and I'm getting 1. So now all I'm going to do is square both sides of this equation. So I get am squared plus bn squared squared equals 1. And now I can use this rule here. If I have two elements in my set A, then I can add them up and square them, and the new number will also be in my set A. So this thing here was in A, this thing here was in A, so I'm adding them up and then squaring them, so this whole thing is in my set A, or in other words, 1 is in my set A, and therefore, by this logic up here, A must be the set of all integers. And that solves our problem. We proved that if m and n are co-prime, and A is an admissible set containing both m and n, then A has to be the set of all integers. And before we proved that if m and n aren't co-prime, we can find an admissible set containing m and n, which isn't the set of all integers. Anyway, I hope you have found this problem interesting and you managed to follow along with the solution. I think this is a really interesting problem which doesn't require too much prerequisite knowledge. Of course, Bézieux's lemma may be here, but apart from that, there's not really too much making this solution difficult to follow, which is occasionally the case with some IMO problems. Anyway, I am waffling now, so I will stop waffling. I will let you go. Thank you for watching. I will catch you in the next one. Have a great day.